Hello all, welcome to the episode 24th in hexadecimal of Debugging TV Friends program. You can type your questions during this episode. If I can't answer particular questions now, I then post answers on the website debugging.tv. The topic of today's episode is manual stack trace reconstruction in the context of the new crash dump analysis pattern called past stack trace. I assume you are familiar with stack traces, or also called in Unix-derived operating systems as backtraces. When a function calls another one during thread execution, a return address is saved in a special memory region called raw stack. Function parameters and local variables are also saved there. This memory region changes dynamically during execution, and the same raw stack area can be written over many times, erasing previously saved data. At any given moment, we call this data execution residue. What is left? There is a corresponding memory dump analysis pattern too, called execution residue. On this picture, for example, we see nested function calls, and on halfway from their return, the thread experiences an access violation. So when we open a crash dump or touch a debugger, we see its current thread stack shown as yellow bracket, and yellow arrows, but we also see past blue arrows, and they are not visible unless we try to analyze the raw stack data, dump some values, and so on. So please also note that stack grows towards low addresses as reflected on address line. Another example here shows the buried past partial stack trace. Such past stack traces might be useful in reconstruction of past behavior, especially when many third-party components were involved, and this is applicable to both user space and kernel space analysis. I decided to model this situation by writing a small program. I put its source code on debugging.tv afterwards. So let's go to Visual Studio. So this is a small program. I used macros to save on coding. So basically we see main procedure here. It calls foo function. So, and then we get this nested stack trace. Not stack trace, but the sequence of nested calls from foo to foo underscore 1, foo underscore 2. So like 10 functions are called. One function calls another, and so on. And then all this goes back, returns to foo, and we call bar function, and we get another nested sequence of calls. And I also put some local variables for each function in order to get some real stack frames, and also notice here I put some array of 4,000 integers. Is just to make room for crash. We see here what we see here is, for example, here we get, when we call bar, it finally reaches and calls abort function. And so to make some room for crash dump processing functions, the first foo function allocates some memory. This is all done to have this past stack trace located far away from crash dump processing so that it doesn't overwrite past stack trace. So anyway, all this better seen in WinDBG. So if we compile this program for both 32-bit and 64-bit modes, so we get two applications. So we run them and they crash. So two crash dumps were created, saved, and so what I did, I already opened them in WinDBG, and first we look at 32-bit crash dump. I open log file, and first I fix symbols, Microsoft symbols, and do reload. So this is all done on the same developer machine. So we get the current stack trace with source code. We can use KL capitalized to remove source code references. You see we have the current stack trace, so main function calls bar, bar calls bar underscore 1, and so all goes until we see abort. I also could have put access violation here, for example. So let's now dump raw stack. This can be done. So we get stack trace, stack region, boundaries from thread environment block. Use the ps command. So if we scroll down a bit, so first we see all these bar frames. So if we scroll a bit up, past abort and exception processing, you see that Windows error reporting calls. So this is why we needed extra space for the first foo function call. And then if we go up and skip, we find some region with foo. So this is our past stack frames. It happened in the past. They are not overwritten. So basically we can do manual stack trace. You see, because it's a 32-bit dump, we have standard. There's no optimization here, so we have that each address here points to saved EBP register, and you see it points to the next frame. From here we see this address, also saved EBP, points here to this address. So in this way all this can be linked together into stack trace. So this can be done manually, or we can give a hint. For example, here what hint can be given. So we can take this address and supply it as a hint to K command to give us new past stack trace. So I basically specify 3 values for frame pointer, stack pointer, and instruction pointer. You can check this version of command from WinDBG help, and I specify L just not to see source code. And you see what we have now. We have a partial stack trace, but it also past stack trace, but it also nicely glued to main function. So we also see not a truncated stack trace as usually we get when we get past stack fragments, but it nicely glues to main function till the thread startup functions. And we can do the same, get the same stack trace if we, for example, remove PDB file and then we do reload. Then we get the current stack trace. You see, all without symbols. We just get module name. But the same procedure helps because, for example, if we dump the same raw stack region, you can scroll. You see, we also get similar linkage between frames, and so we can try to supply some pointer and also get partial stack trace, but without symbols. And stack trace seems to be valid because we end up with thread startup functions. Okay, and now we analyze the same program was compiled for 64-bit. So we get another dump. So I open log file. I later post log files on debugging.tv. And we fix symbols. Do reload. And because this is a developer machine, so we get the same good stack trace with symbols. So we see the same current stack trace with bar functions, just pointers 64-bit. And when we get raw stack region and look at it, and scroll a bit up, we find some stack frames, although they are not very they do not seem to be linked in the same way, because RBP register is not used as stack frame pointer for 64-bit. Nevertheless, we can still use the same hint, but now we point to, for example, to the return address and use the same form to get past stack trace. Also, you see it is nicely glued with main function, but what happens if we try to get any other? So for example, let's say we try to specify this pointer. You see we get some sequence of return addresses, but this is not correct past stack trace, we think. First of all, it doesn't have any thread start, user thread start or other functions, and also always use your judgment, like semantics of stack trace. For semantics of stack trace, like for example, sometimes you can see a heap function and then it calls create process, so this can't be. So for example, let's try another address. So it seems to be here we are able, so we just took some address and we were able to get current stack trace. But we can also take any other address just for a test. And so you see, though, if you're not sure which address to supply, you can always try different values and see whether you get good stack trace, which can be semantically sound, even if it doesn't have any thread startup calls, like this. Okay, so this is all as for demonstration. Let's go back to presentation. So on this slide I put stack traces, the current stack trace, and one stack trace we got from past execution residue, past stack trace. So here on this slide I put relevant pattern descriptions, relevant pattern links to pattern descriptions, and they can be found in software diagnostics library. Glued stack trace pattern can be used to join partial past stack trace fragments, or a past fragment with a part of the current stack trace, like we have seen. And I also did a similar exercise in the past for macro 6. So for this, please check episode F from Debugging TV. And finally, this is the usual add slide of upcoming training sessions and free webinars. 2 courses are available in July for booking now: Live Debugging 3 training course and the updated version of Accelerated Windows Memory Dump Analysis training course. There are a few webinars too. Next month we plan to talk about the philosophy of software diagnostics and in June about application of software narratology and software trace analysis patterns to network trace analysis. And so thank you for watching this episode. Please later check out the slides and recorded video from debugging.tv. I also post source code and logs. And the next episode should be next week, hopefully. We try to come up with something from kernel space side, because most episodes were, I would say all episodes were from user space, so I try to come up something from kernel space side. Okay, thank you. Bye bye.